Okay, so the situation presented before us is just before 6 p.m., students enter the classroom to find Mr. Fees dead of an apparent homicide. Everyone said they saw it coming. At 6, the temperature of the body is 80 degrees, while at 7 p.m., it was 70 degrees. It took a while for the campus police to get through the party. If the room is kept at a constant temperature of 70 degrees Fahrenheit, what is the time of death? Okay, so the important information to take away from here is that at 6 p.m., the body was 80 degrees, and at 7 p.m., the body had lowered to 75 degrees. That means in that time period, being 1 hour, the temperature of the body decreased by 5 degrees Fahrenheit. And the whole time, the room was kept at a constant 70 degrees Fahrenheit. In order to solve this problem, we need to use Newton's law of cooling. It consists of the temperature of the object at the end, the temperature of the room, which is the ambient temperature, the temperature of the object initially upon discovery, and then K, the decay coefficient, as well as little t for time. In order to determine the time of death, we must first solve for K. To do so, we'll have to plug in all known values. The temperature of the body after being discovered was 80 degrees, so our initial temperature will be 80. 1 hour after discovery, the police had arrived, and the body's temperature had decreased to 75 degrees. So our final temperature will be 75, and our time elapsed will be 1 hour. The temperature of the room is a constant 70 degrees, so our ambient temperature will be 70. After plugging in all those values and simplifying, we are left with 75 is equal to 70 plus 10e to the power of negative k. Our goal now is to try and get e with the exponent by itself. So we're going to subtract both sides by 70, then again, we're going to divide them by 10, leaving us with 1/2 is equal to e to the power of negative k. Once e is on its own, we can check the natural log of both sides so that we are now able to interact with the exponent. This gives us the natural log of 1/2 is equal to negative k. Now all we have left to determine k is to divide both sides by -1. Because k is originally equals an irrational number, I'm going to keep it equal to the negative natural log of 1/2 because we will have to reuse it again. So from this point on, I'm just going to refer to negative natural log of 1/2 as just k. Now that we have solved for k, we can now determine what the time of death was. So we know that the initial temperature of the body was 98.6 because that is the temperature of a living body. And then the body was discovered at 6 p.m. to be 80 degrees. So our initial temperature is going to be 98.6 and our final temperature will be 80 this time. Since we do not know the time, we will not put in anything for t because that is what we are solving for. Then, once we have all our inputs plugged in, we will simplify both sides, and that leaves us with 80 is equal to 70 plus 28.6 times e to the power of negative kt. Then we'll subtract both sides by 70 once again, and then divide by the coefficient of e, which is 28.6. This leaves us with 10 divided by 28.6 is equal to e to the power of negative k times t. Now that e is alone on the right side, we can take the natural log as we did before, and that'll allow us to interact with the exponents, giving us ln times 10 divided by 28.6 is equal to negative k times t. Now that we're able to interact with the exponents, we can divide both sides by negative k to find the exact time that elapsed. Once again, the variable led to an irrational number, so I rounded to the nearest tenth to get 1.5 hours. 1.5 hours is equal to 90 minutes. So to determine the time of death, we must subtract 90 minutes from the time the body was discovered to determine the time of death, which is 6 o'clock minus 90 minutes is equal to 4:30. So now we know that the body had died roughly around 4:30.